So we have this idea for what it will mean for two vector spaces to be isomorphic, right? For an isomorphism to exist between them. An isomorphism is a function that's between vector spaces that's one-to-one and onto, and also satisfies these properties, right? It turns vector operations in one vector space, in the domain vector space, into vector operations in the range vector space, like this. Incidentally, this property often gets called, or it's described by saying that F preserves structure, or preserves vector space structure, right? Because the idea is if you don't have an addition and a scalar multiplication, you don't have vector spaces, you just have sets. And so it's the addition and the scalar multiplication that gives the vector space its structure as a vector space. And so that's why we're using this phrase structure. All right, so let's look at some examples of isomorphisms. So here's one. This is one of the two examples that inspired us to define isomorphism. So the function from P2 to R3, where you just take the coefficients from a polynomial of degree less than or equal to 2 and then make a vector out of them, a 3-entry vector. This is actually slightly different than the one that we looked at before because the entries are in the other way. But it's still an isomorphism. So I won't prove this in detail, but is this onto? Well, yes, you can see that no matter what entries are in your vector, it's possible to put the same coefficients on a polynomial, and then f of that polynomial will be that vector. So onto, yes. Is it one-to-one? Well, probably you can see that if you have two polynomials and they have the same output, well, the only way that can happen is if the polynomials had the same coefficients to begin with, but polynomials that have the same coefficient are equal polynomials. So, right, if the output of this function is the same, that implies that the input was the same to begin with, and that means it's one-to-one. And then for preserving structure, we actually went through the argument of why this function preserves structure in an earlier video, so you can check on that. So it does preserve structure. So this is an isomorphism. All right, similarly, our second example that inspired us to define isomorphism was this function from the vector space R4 to the vector space of 2x2 matrices, M22. And this function essentially just, this should be G here. This function essentially just reshapes the column vector into a 2x2 matrix. And again, I won't write out the details, but is it onto? Well, yes. No matter what the output is, you can find an input that has that output just by rearranging the entries in the right way. Is it one-to-one? Well, if two outputs are the same, then clearly the two inputs were the same, so yes. And then does it preserve structure? Does it turn addition and scalar multiplication in R into addition and scalar multiplication in M22? And again, in a previous video, we saw why that is the case, so yes. So this is an isomorphism. All right, for another example, how about this function from the span of 132 to -101 to R2 defined by this function? Now this is a much harder question because this span is not all of R3, right? So this is going to be a much trickier question. And there are several things to prove. So first, we have to prove that H is well defined. What do I mean by well defined? Well, there's some ambiguity in how this function is defined because, well, there's some apparent ambiguity in how this function is defined because what if there's more than one way? What if for a fixed vector, there's more than one way to choose coefficients on these vectors that produce that vector, right? Then, right, think of, say, this kind of situation, right, there's more than one way to express one of these vectors as a linear combination of all of these vectors. So working just with coefficients of these three vectors is going to be ambiguous because there's more than one way to express a vector as linear combinations of these three. So you have to be careful when defining things in terms of linear combination. But remember, notice that these two vectors are linearly independent, right? Which, since there's only two of them, they aren't multiples of each other, so they're linearly independent. And one important property of linearly independent sets is everything in the span of a linearly independent set can be written as a linear combination in a unique way. So this representation of A times this vector plus B times that vector, this is unique. Right? Every vector in the span can be written in this form in exactly one way, and so there's none of this ambiguity that can happen like I was describing over here. So this definition is well defined. Okay, you need the function to be well defined because otherwise it's not a function, right? Because if a function isn't well defined, essentially what's happening is you could have multiple outputs for one input, but that's not allowed for a function. Okay, so this is well defined. Is it onto? Well, yes, clearly, right? No matter what A and B are, just stick them over here and you've produced a vector in this span that H sends to AB. So yes, onto. Is it one-to-one? This one's a little more tricky. So if, right, what we need to ask is if H of, so I'm going to call this one V1 and this one V2, just so I don't have to write out the vectors. So if A1 V1 plus A2 V2 equals H of, say, B1 V1 plus B2 V2, what we want to prove is we want to prove that A1 V1 plus A2 V2 is equal to B1 V1 plus B2 V2, right? Because then we'll have shown that if you have the same output, then you have equal inputs. So how can we prove this? Well, let's write down what these are. So this H of A1 V1 plus A2 V2 is A1 A2, right? That's just the definition of H. And then on the right-hand side, we get B1 B2. But if A1 A2 is equal to B1 B2, then A1 equals B1 and A2 equals B2. Thus, or therefore, right, this linear combination is equal to that linear combination because these coefficients are actually equal to each other, right? So that shows that this is one-to-one. Now finally, preserving structure. Scalar multiplication is pretty straightforward, so I'll do addition, right? So let's suppose that we have two vectors in this span. That is, two linear combinations of these two vectors. So if we have, say, A1 V1 plus A2 V2, right? Here's one linear combination in that span. Here's another, B1 V1 plus B2 V2. Okay, if we add these, this addition is in that span, right? So then we do H of this. What we're hoping is that we get H of A1 V1 plus A2 V2 equals, plus, and this addition is in R2, H of A1 V1 plus A2 V2. B1 V1 plus B2 V2. Okay. So, right, this is what we're hoping to get, but we have to do a calculation. So, we can do this addition, first of all. What we get is A1 plus B1 V1 plus A2 plus B2 V2. And now we can calculate H. And this is A1 plus A2. I'm sorry. No. A1 plus B1. There we go. A2 plus B2. Right? Well, now we can compute what is all this stuff. Is it the same as that or not? Well, let's calculate. So H of A1V1 plus A2V2, right? H just picks off the coefficients and stuffs them into a vector like this. Okay, and then H of B1V1 plus B2V2, that's B1V2. And then if we, right, and this addition is in R2, if we do this vector addition in R2, we do indeed get that. So this shows that vector addition is preserved. Okay, now we also need to show that scalar multiplication is preserved, but that one is actually easier, so I'll let you work that one out. So this shows that this function from this span, which is a subspace of R3, to R2 is actually an isomorphism. You can see that there's actually a lot to prove, right? First, we need to know that the function actually is a function, so it's well defined. Then we have to show it's a one-to-one correspondence, which means we have to show it's onto and one-to-one. And then we have to show it preserves structure, which is another two things. You have to show it preserves addition and scalar multiplication. So having an isomorphism gives you a lot of information, but the flip side of that is showing that you have an isomorphism is a lot of work, at least at first. One of the things that we'll do, incidentally, is figure out better ways of noticing isomorphisms, because proving all of these things individually is a ton of work. Just to look at some examples of things that aren't isomorphisms. How about this function? So it definitely is well defined, right? No question there. So we can check, is it onto, is it one-to-one, does it preserve vector space structure? Now, I won't prove it, but it does preserve vector space structure, so that seems hopeful, but it's not really obvious looking at it, but in fact, this is not onto. So how do you check that? Well, if we can come up with a single vector in R3 that this function does not produce as an output, then that will show that this is not onto. And in fact, 1, 0, 0 is never output by this function. How could you show that? Well, what you can do is, right, you might notice that this formula for the output is actually just a times 2 minus 1, 3 plus b times minus 3, 1, 1. And what we can do is show that 1, 0, 0 is not in the span of these two vectors, 2, minus 1, 3, and 3, 1, 1. If 1, 0, 0 isn't in this span, then that means it's never produced by this formula, but that means it's never produced as an output for this function. Of course, to show that 1, 0, 0 isn't in this span, you can take these two vectors, 2, minus 1, 3, minus 3, 1, 1, 1, 0, 0, and do a row reduction and interpret the results. So this function, even though it looks so promising because it preserves vector space structure, it's not onto, so it's not an isomorphism. All right, how about this one? So here is a function from P2 to R defined by, so g of some polynomial, you just plug in 2, right? This produces a real number as an output because P is a polynomial and we're plugging in a real number. So this function g does produce a real number as an output. In fact, it also preserves vector space structure, which again I won't prove, but it's not hard to prove. So also it's clearly onto because, if you look at, there's always some degree 2 polynomial that produces any real number as an output at x equals 2. So it's definitely onto. Is it one-to-one? Well, Clearly not. I mean, there's more than, just for an example, so 1 to 1, no. So we need to provide a counterexample to show that it's not 1 to 1. Well, x minus 2, so if we take g of x minus 2, remember what g does is it just plugs in 2 to this polynomial, so when we do that we get 0. But there are other polynomials, degree 2 polynomials, that give us 0 when we plug in 2. For example, 1/2 x minus 1 also produces 0 when you plug in 2. Or x minus 2 squared also produces 0 when you plug in x equals 2. So this function g is not at all 1 to 1, so it's not an isomorphism. Okay, so there's an example showing one that fails to be an isomorphism because it's not onto, one that fails because it's not 1 to 1. How about one that fails because it doesn't preserve structure? So let's consider the function from M12, so these are 1 by 2 matrices, which are row vectors essentially, to R2, given by this formula. So h of AB is a cubed and b. This is onto. I won't prove it, but it is, because the cube function is onto and because this function is onto from real numbers to real numbers, h is onto. And by the same token, it's 1 to 1 because the cube function is 1 to 1 and the identity function is 1 to 1 on real numbers. So it is onto and 1 to 1. Does it preserve vector space structure? Well, you know, as usual, preserving vector space structure is a universal claim. So to disprove the universal claim, we need just a specific counterexample. And it's not hard to find one. So for example, how about 2, 0, and 2, 0, right? If we add these, so let's add these two in R2 and then do h afterwards, what do we get? Well, if we add them in R2, we get 4, 0. And then if we hit it with our function h, so 4 to the third power is 64, I think. And then it just copies the second entry, so 0. Okay, so now let's compare that to doing h on these two vectors individually and then adding them in R2. H of 2, 0. Right. In this first calculation, this addition is in M12. Okay, so now we'll do h first and then add in R2. So h of 2, 0 is, right, 2 cubed is 8, and then 0, and then add in R2, 2 cubed is 8, and 0. So this gives us 16, 0. And these are not the same, right? So does this preserve structure? No. Here's a counterexample, right? So you can see having an isomorphism is a very special thing. There are lots of things that can go wrong that prevent a function from being an isomorphism. So isomorphisms are very special objects, special kinds of functions.